Hello everyone. In previous video lecture we have given you introduction of scheduling algorithms. Today we are going to discuss shortage of first and shorted remaining time first algorithms. So these are scheduling algorithms. Quickly let us go through the scheduler. We have already given introduction of scheduler and some terminologies of scheduling. So scheduler basically decide which process to execute. So it selects the process in the memory that are ready to execute and allocate the CPU to one of them. So aim of the scheduler is it minimizes waiting time, it maximizes CPU utilization, it maximizes throughput. We measure by number of processes that are complete per unit of time. Then we minimizes response time, and in fairness we give fair chance to every process. These are some of the terminologies which we required for scheduling algorithms. So we have already given you introduction of this: turnaround time, start time, completion time, and throughput. We are also going to call this as a TAT, then arrival time, completion time is your CT, and we are going to calculate throughput and response time based on the given parameter. So waiting time is the sum of the period spent waiting in the ready queue. So here we are basically scheduler, what it does is we are having number of processes in the ready queue. So it gives a chance to process to execute on the processor. So there are different strategies. So one of the strategy, as I said, is shortage of first. So with the help of scheduler, we are going to maximize CPU utilization and throughput, whereas our aim will be we will minimize turnaround time, TAT, waiting time, and response time. Now there are two types of scheduling algorithms. There are two schemes, those are non-preemptive and preemptive. So in non-preemptive, once CPU has been allocated to a process, the process keeps the CPU until process exits after completion of its task or process switches to waiting state. Whereas in preemptive approach, process can be interrupted and it must release the CPU. For example, process P1 is given to the processor, then with preemptive approach, we'll preempt the process P1 and we'll give a chance to next process, might be P2. So whereas here in non-preemptive, we are not going to preempt any process, we will allow that process to finish its task. So let us start with the shortage of first. So here we are going to consider burst time for this algorithm, and also we are going to decide one decision mode that is our approach, that is non-preemptive. Let me quickly tell you which are the preemptive algorithms and non-preemptive algorithms. So already we have seen FCFS, which belongs to non-preemptive, so we are not going to preempt the process. Whereas, let us say that FCFS and shortage of first are non-preemptive algorithms, whereas round robin, priority scheduling algorithm, and version of SJF, that is SRTF, is also called as are also preemptive algorithms. So if you look at here, as I said quickly, we are going to take burst time of further shortage of first and decision mode, that is non-preemptive. So number of processes will be given to you, their arrival time will be given to you, and burst time will be given to you. We have already seen these terminologies like arrival time and burst time before. And our aim is to calculate the waiting time and response time. So let us look at the example, how to solve this, how to go for the example. So 4 processes are in the queue, they are ready to execute. So arrival time of process P1 is 0, arrival time of process P2 is 2, process 3 is 4, process P4 is 5. Whereas this is the CPU burst time. For P1 it is 7, P2 4, P3 1, and P4 4. As I said, we are going to consider the burst time, and our algorithm is shortage of first. So the process which is having the shortest burst time will get the preference. So let us try to solve this numerical with the help of one Gantt chart, and we'll also maintain a ready queue for these processes. So let us start at time 0. Let us check how many processes has arrived. So at time 0 only process P1 has arrived. So let us maintain this P1 into the queue and let us schedule this P1 for its execution. Now for how long this P1 will execute? So P1 will take its burst time, that is 7. So process P1 will execute for 7 units of time. Now by the time 7, how many processes has arrived? By the time 7, P2, P3, P4, all processes are arrived. Look at the arrival time of these processes. So let us bring all of them into the queue, P2, P3 and P4. Now P1 has finished its task, so it will be out of the queue. So among this P2, P3, P4, as per our criteria, we are going to consider a burst time. So which process is having the burst time? We have to decide that. So P2 is having 4, P3 is having 1, and P4 is having 4. So P3 will get the preference because its burst time is 1. So here the time taken by P3 will be 8. 7 plus 1, that is 8. So P3 has finished its task. So in our queue, there are 2 processes left, that is P2 and P4. Now if you look at here, burst time of P2 is 4 and burst time of P4 is 4. So both are same. So which process to schedule next? For that again we have to decide one strategy. We will consider arrival time of those processes. So if you look at here, P2 is having a burst time 4, but its arrival time is 2, whereas P4 is having burst time 4, same, but its arrival time is 5. So P2 has arrived first, so we will schedule P2 first before P4. So burst time of P2 is 4, so 8 plus 4, it will take total 12 units of time for the execution. Now the last process that has left into the queue, that is P4. Now burst time of P4 is again 4. So time taken by P4 to complete the execution is 12 plus 4, that is 16. Now this Gantt chart, now P4 has executed its task. So all processes has finished its execution. So now with the help of this Gantt chart, let us try to find out the completion time of respective processes. So P1 has completion time, that is 7. P2 has completion time, that is 12. P3 has completion time, that is 8. And P4 has completion time, that is 16. Now these are the completion times we have calculated as per the processes. Let us go for calculating turnaround time and waiting time. Now how to calculate the turnaround time? Turnaround time as per the definition we have seen, it will be completion time minus arrival time. So 7 minus 0, P1, turnaround time for the P1 it will be 7, and for P2 it will be 12 minus 2, it will be 10. For P3 it will be 4, and for P4 it will be 16 minus 5, that is 11. Now how to calculate waiting time? How much P1 has taken time in the ready queue while waiting. So for waiting time we will consider turnaround time minus burst time. So turnaround time and burst time, with the help of burst time we will calculate waiting time for P1. So it is 0. For P2 waiting time is 10 minus 4, that is 6. For P3 waiting time 4 minus 1, that is 3, and for P4 waiting time is 11 minus 4, that is 7. Now we are done with the turnaround time and waiting time. Let us calculate average waiting time and average turnaround time. So average waiting time is, it is 16, whereas average waiting time is 16, and we have total 4 processes. So 16 divided by 4, it will be 4, will give the units for time, that is 4 milliseconds. So let us go back to our example. So you will get Gantt chart in this way. It is for P1 it has taken average waiting time, if you look at here, it is 0 plus 6 plus 3 plus 7 is 4 ms. So if you compare this shortage job first with the FCFS, you will come to know that this is more optimal than the FCFS. So why it is more optimal? Because the SJF scheduling is specially appropriate for batch jobs for which runtimes are known in advance. Because since the SJF gives the minimum average time for a given set of process, it is optimal. So average waiting time given by the SJF is 4 milliseconds, which is lesser than the FCFS. I hope this is clear to you. Similarly, we will also calculate average turnaround time. Now, this is the preemptive approach of shortage job first, for which we will also give a name, that is SRTF, shortest remaining time first. So, like shortage job first, but running job can be preempted. So, in previous example, we were not preempting the process, we were allowing that process to finish its burst time. But here we are going to preempt the process because we want to give a fair chance to every process. We don't want to keep CPU idle for longer time. So let us take example. Now same example we are considering. So 4 processes are there, their arrival time and burst time, and we will be calculating completion time, turnaround time, and the waiting time. So if you observe, we are again going to draw a Gantt chart, and we are going to maintain a queue for these processes. So let us consider the process P1. So it has arrived at 0. So let us schedule this P1 for its execution. Now here P1 is taking a longer time. If you observe here, the P1 is going to take 7 CPU burst time, whereas P2 is smaller than P1, P3 is even more smaller than P1, P4 is also smaller. But P1 is taking a longer time initially, so what we will do, as per our strategy, we are going to preempt the process, and then we are going to give a chance to other smallest processes. So let us bring that P1 into the queue because P1 has arrived at 0. What we will do is, we will give only 1 unit of time for this process to execute. So we have given 1 unit of time to P1. So the burst time remained for P1 is 6. Now P1 has arrived. So by the time 1, how many processes has arrived? So by the time 1, no one has arrived yet. So we'll give a chance to P1 again to execute its task for 1 more unit. So here it will be 2. Now by the time 2, let us check how many processes has arrived, and now here it will become 5. So by the time 2 process P2 has arrived, so let us bring this P2 into the queue. It is ready to execute. Now let us schedule this P2 as per our policy. Let us schedule this P2 for 1 unit of time. So here it is 3, 2 plus 1, 3. Now by the time 3, how many processes has arrived? So by the time 3, only P1 and P2 has arrived. So let us give a chance to P2 again to execute. So P2, it will become here, it will again execute for 1 unit of time. So P2 becomes 2. So by the time 4, P3 has arrived. So let us bring this P3 into the queue. Now let us compare shortest time among these processes, P1, P2, P3. P1 is having 5 unit of time, burst time. P2 is having 2 unit of time, and P3 is having just 1. So let us give a chance to the newly arrived process, that is P3, to execute. So we are going to give again 1 more unit of time for execution. By default, P3 is having only 1 unit of time, so here it is 5. Now by the time 5, let us check how many processes has arrived. So by the time 5, P4 has also arrived. So let us give a chance to P4 to execute. So we are going to schedule P4 now for 1 unit of time. So P4 is having burst time, that is 4. So for 1 unit of time, P4 will execute, and it will become 3 over here. So if you look at here, So P4 is having let us not give P4 will not have okay. So by the time 5 P4 has arrived, we have to compare burst time of all these processes. So P1 is having burst time 5, P2 is 2, P3 has already completed its task. So P3 has already completed its task, so it will come out of the ready queue. Now let us check available processes. So these are P1, P2 and P4. So burst time of P1 is 5, burst time of P2 is 2 and burst time of P4 is 4. So as per our policy shortest remaining time first, what we will do? We'll compare burst time, so 5, 2 and 4. So 2 is having the smallest burst time. So let us schedule P2 next. And now we will not give only 1 unit of time for P2 because now all the processes has arrived in the queue. So P2 will finish its task. So only 2 units are left for P2. So 5 plus 2. So P2 will take 2 units of time. It's 2 units of time and it will run for its completion. Now P2 has completed its task, so it will come out of the system. So how many processes has left? So only 2 processes has left, that is P1 and P4. As per our policy, again we are going to compare burst time of P1 and burst time of P4. So which one is having the smallest time? Burst time, that is P4. So let us schedule P4 next. Now how long this P4 will execute? P4 is having 4 units of time, so it will take 7 plus 4, that is 11. So 7 plus 4, that is 11. Now P4 has finished its task, so the process which has left, that is P1. So P1, what is the burst time of P1? It is 5. So 11 plus 5 is 60. Now all the processes has finished its task. So Gantt chart is available to us. So even P1 has finished its task. So let us write completion time of P1, completion time of P2, P3 and P4. So when P1 has finished its task, after time 16, it has taken 16 units of time for its execution. When P2 has finished its task at time 7, it has finished its task. When P3 has finished its task, it has finished early than P2, so it has taken 5 units of time. When P4 has finished its task at time 11, it has finished its task. So we have calculated completion time. Let us calculate the turnaround time. So how we calculate turnaround time? So again, as per the definition, completion time minus arrival time. So completion time is 16 for P1, 16 minus 0, turnaround time is 16. Completion time of P2 is 7 minus 2, that is 5. Completion time of P3 is 5 and arrival time is 4, so it is turnaround time is 1. P4 11 minus 5, so it is 6. Now let us calculate waiting time for these processes. So how long P1 has waited in the ready queue? So waiting time, how we calculate? Turnaround time minus burst time. So burst time is 16 minus 7, so that is 9. Again 5 minus 4, that is 1. And 101 minus 01, that is 00. And then, for example, P3 has arrived here at 4 and it has taken its 1 unit of time and it has finished in given time. So waiting time is 0 for P3 and for P4 it is 2. So now our aim is to calculate average waiting time for the given processes. So average waiting time is 12 and total number of processes are 4, so 12 divided by 4 is equal to 3 milliseconds. So this approach is preemptive approach, where we are going to preempt the processes. We have tried to give a fair chance to every process. So long process which are having longer burst time should not take control of CPU for longer time, whereas other processes should get the fair chance to execute. So let us go back to the answer. So if you look at here, this is the Gantt chart available. So P1 has finished at 16, P4 11, P2 has finished at 7, P3 arrived at 4 and finished at 5. So average waiting time for this processes is 3 milliseconds. So in preemptive approach, this SJF is optimal because it's moving a shorter process earlier always decrease short process. So waiting time more than it increases longer process wait time. So that's all for shortest of first and shortest remaining time first. I have taken a few more examples as an exercise. So this example you can solve using non-preemptive approach. Strategy we are going to use is shortest of first. So as I said, criteria we are going to consider that is burst time, and decision mode I have given that is non-preemptive. So this is the example, 5 processes as given with their arrival time and burst time. So you have to start with the Gantt chart, you have to also maintain the processes into the ready queue, and then just try for completion time, turnaround time and waiting time. Similarly, this is one more example which you can solve with the shortest remaining time first algorithm, so which is the preemptive approach of SJF, so in which you are going to preempt the process. So again, criteria, you are going to consider burst time with the processes which are having the shortest burst time, but you will preempt just to give a fair chance to the other processes. That's all from my side. Thank you.